May 15, 2001. A 47-car freight train is tearing across northern Ohio at over 50 miles an hour. Nobody was on board and it ran for 66 miles. No driver. No effective brakes. No way to stop it. They called it Crazy Eights. Buried in that consist were 2 tank cars carrying molten phenol, a toxic industrial chemical that, on derailment, could blanket a populated area in a lethal cloud. This isn't a runaway train story. It's a chemical disaster countdown. And the whole thing started with the most routine yard move a 35-year veteran had ever been asked to make. On May 15, 2001, CSX Locomotive 8888, popularly dubbed Crazy Eights, escaped all human control. The 47-car freight train weighed nearly 2,900 tons, pulling 22 loaded cars and 25 empties. For the next 2 hours, this massive steel consist surged southward across northern Ohio. Nobody was on board, and it ran for 66 miles. To understand this movement, it helps to look at the braking systems. When investigators noted the train had no brakes, they did not mean the physical hardware was missing. The train was equipped with standard air brakes, but the air hoses connecting the main locomotive to the trailing 47 cars were disconnected. This was standard practice for quick yard moves, but it meant the train-wide emergency brakes were completely isolated. No air pressure could travel down the line to trigger them. The locomotive's own independent brake was fully applied, but the control stand was set to full power. At throttle notch 8, the 3,000 horsepower diesel engine easily overcame the grinding friction of its own brake shoes, heating the metal to extreme temperatures. The safety alerter, designed to halt an unmanned train, was completely deactivated because of this specific independent brake pressure configuration. With no driver, no air connection to the trailing cars, and the engine screaming at full power, the train accelerated past 50 miles per hour. It was a massive rolling force heading straight toward populated towns, pulling cars loaded with a highly toxic cargo. The weight of the train was only half the danger. Coupled within the consist were 2 tank cars, each carrying thousands of gallons of molten phenol. In industrial production, phenol is used to manufacture plastics, pharmaceutical products, and dyes. But in its raw, concentrated state, it is a highly toxic, corrosive, and flammable compound. It causes severe chemical burns on contact, and breathing its vapors can quickly become fatal. Because the substance must be kept hot to stay in its liquid form, it was transported at temperatures exceeding 200 degrees Fahrenheit, meaning any breach of the tanks would likely result in an immediate, toxic fire that would resist standard extinguishing efforts. This isn't a runaway train story, it's a chemical disaster countdown. The tracks ahead did not cut through empty wilderness. The train was now hurtling south down the Toledo branch, an active rail corridor running directly through the middle of multiple northern Ohio communities. The path led straight toward Bowling Green, Findlay, and Kenton, towns where homes, schools, and local businesses sat just yards from the rails. At 50 miles per hour, any sharp curve or minor track defect could trigger a derailment. A crash would rupture the steel tanks, releasing a lethal chemical cloud into residential neighborhoods and forcing massive, high-speed emergency evacuations. Every public crossing became a potential point of impact, transforming a simple yard error into an active threat to thousands of lives. Walbridge Yard, located near Toledo, Ohio, serves as a massive classification hub where hundreds of freight cars are sorted and reassembled daily. On the morning of May 15, 2001, the atmosphere inside the facility was entirely ordinary. A 3-person local crew reported for duty to perform routine switching operations. The team consisted of a conductor, a brakeman, and an engineer. The engineer was a 35-year railroad veteran, first hired by the Pennsylvania Railroad in 1966. Throughout his career, he had maintained a clean safety and disciplinary record, earning a reputation as a reliable and capable worker. There was no indication that his shift that day would be any different from the thousands of others he had successfully completed. The crew's assignment was straightforward. They needed to complete a short, routine yard move, shifting a string of 47 freight cars between tracks. To pull this consist, they used CSX Locomotive 8888, a standard EMDSD 40-2 diesel-electric locomotive. This type of low-speed movement within yard limits is a fundamental part of daily railroad operations. Because the cars were only being shuffled across short distances, the crew kept the train-wide air brakes disconnected, a standard approved practice to save time during quick yard switching. At this stage, the task was a simple, low-risk piece of housekeeping. Nothing about the weather, the equipment, or the crew suggested that this routine morning shift was about to change. The yard crew was shifting cars when the engineer noticed a misaligned track switch ahead. Deciding to line the switch himself, he prepared to step down from the slowly moving locomotive. To keep the train's speed in check while he was on the ground, he reached for the control stand. His plan was to engage the dynamic brake. On this EMDSD 40-2, the controls govern two opposite forces. The throttle controls motive power, feeding fuel to the diesel engine to pull the train forward. The dynamic brake uses the traction motors to generate electrical resistance, fighting the rolling wheels to slow them down. It is the difference between active pull and heavy resistance. To switch from power to braking, the engineer had to move a separate selector handle into the braking position. He believed he had made this adjustment. He then pushed the main control handle forward, expecting the electrical resistance to hold the train at a crawl. But the selector had not clicked over. It remained set to power. By pushing the handle forward, the engineer did not initiate braking. He advanced the throttle to notch 8, commanding maximum forward power. Instead of a dragging anchor, the engine received a sudden surge of 3,000 horsepower. As the veteran engineer stepped out of the cab and onto the ground, the train did not slow down. It began to pull away, accelerating under full power with its cab completely empty. The diesel engine roared as the train surged forward. The engineer chased the accelerating cab, reaching for the grab irons. He caught the handrails, trying to pull his body back up the steps, but the 3,000 horsepower locomotive was gaining speed too fast. The train dragged him 80 feet along the rocky ballast as he clung to the side, trying to reach the door. His grip failed. He tumbled onto the gravel, escaping with minor scratches, as the massive steel frame pulled away into the distance. By the time he stood up, the train was already moving faster than any human could pursue. With the cab empty and the controls set to full power, the machine was completely on its own. A locomotive uses two distinct braking systems. The first is the automatic brake, which commands the entire train. It relies on a continuous air pipe running from the engine all the way to the last car. When pressure in this pipe drops, air reservoirs on each individual car trigger the brakes. But during routine yard moves, connecting and testing these hoses for dozens of cars takes hours. To save time, crews operate in an air-off configuration, leaving the air hoses between the locomotive and the freight cars disconnected. While this is a standard, authorized practice, it meant the train-wide automatic brakes on all 47 cars were completely isolated. They could not be used. This limitation was a consequence of the temporary yard setup rather than a design flaw of all freight trains. But in this specific instance, it left the consist without its primary stopping mechanism. That left only the independent brake, which acts primarily on the locomotive itself. When the engineer stepped down, he had set this brake to full capacity. But a single locomotive's physical brakes cannot hold back a 3,000 horsepower diesel engine screaming at full throttle. The brake shoes pressed hard against the spinning steel wheels, but the immense power of the engine forced them to turn anyway. The friction generated intense heat, rapidly wearing down the metal and destroying their stopping power. Normally, an automated safety system called the alerter acts as a dead man switch. If the controls are not adjusted for 40 seconds, a loud alarm sounds. If the engineer fails to press a button to prove they are awake, the system automatically cuts engine power and applies the brakes. But the system had an unrecognized vulnerability. The design of the alerter logic dictated that if the independent brake cylinder pressure was high, specifically above 20 pounds per square inch, the engineer must be actively operating the locomotive. Consequently, the high brake pressure automatically deactivated the alerter. The very act of securing the locomotive with its own brakes had silenced the only safety backup on board. With the automatic brakes disconnected, the independent brakes melting, and the alerter disabled, the train was entirely on its own. As the driverless freight train sped south toward populated areas, railroad workers and emergency responders realized they had to physically force the train off the tracks before it reached a major town. The first physical intervention took place near Kenton, where rail crews hurried to the tracks ahead of the oncoming locomotive to install a portable derailer. A portable derailer is a heavy steel wedge clamped directly onto the rail. It is designed to lift the wheel flange of an errant car or locomotive up and guide it off the railhead, intentionally causing a controlled derailment. But this tool has very specific operating limits. It is designed for low-speed protection in yards or industrial sidings, built to stop slow-rolling cars from drifting onto active main lines. CSX 8888 was not drifting. Driven by 3,000 horsepower, the 2,900-ton train was traveling far too fast for a portable device to contain. When the massive locomotive hit the steel wedge, the immense kinetic energy of the speeding train easily overcame the clamp. The locomotive did not derail. Instead, the leading wheels simply smashed straight through or threw the heavy metal device aside, barely feeling the impact. The failure of the derailer was not a mistake by the crews, but a limitation of the tool itself under extreme conditions. The simplest physical option to stop the train had been tried, and it had failed completely. The runaway continued south, completely unchecked. The Ohio State Highway Patrol took positions along the tracks to attempt a direct tactical intervention against the moving locomotive. Sergeant Tom Gwynn and Trooper Al Leitenberger pursued the train by patrol car as it surged down the line. Their target was a small red button mounted on the side of the engine frame, the external emergency fuel cutoff switch. Pacing the train, the officers fired 3 shotgun rounds at the target from their moving vehicle. Slugs struck the locomotive, but the engine did not slow down. The external cutoff is a safety feature designed to starve the diesel engine of fuel, halting combustion. It is strictly an engine shutdown option, not a remote brake application. Even if successful, it would not have stopped the train instantly. It would have merely allowed the 2,900-ton consist to slowly coast to a halt. The engine continued to roar at full power because the shots missed the mechanism. Forensic inspections later revealed that the slugs hit the larger red fuel cap located right next to the recessed shutdown button. The protective cap was damaged, but the fuel line itself remained completely intact. The locomotive continued to draw diesel from its massive 5,000-gallon tank, its power uninterrupted. The highly unusual attempt to disable the train from the ground had missed its mark by inches, leaving emergency responders out of standard options as the train sped toward the next town. The failure of the portable derailer and the missed shots at the fuel cutoff exposed a stark operational reality. Standard emergency procedures were never designed for a heavy freight train running under maximum locomotive power. Every tool in the playbook relied on flawed assumptions. The portable derailer is built for yard protection, operating on the premise that a runaway would be rolling at low speeds, lacking the massive kinetic energy to simply throw the wedge aside. The external fuel cutoff switch assumed ground responders could reliably access and hit a precise physical target on a locomotive screaming past at over 50 miles per hour. More importantly, neither attempt solved the core crisis. A tripped fuel cutoff only starves the engine, leaving 2,900 tons of steel to coast for miles on momentum. A derailer simply trades a runaway for a high-speed wreck. Neither option could actually command the brakes or provide entry into the empty cab. At this point, ground-based interventions were completely exhausted. Responders had no remote override, and no single command could shut off power and apply train-wide brakes. The train's continuing power and its immense momentum remained two separate problems, with no unified solution from the ground. With the safety playbook empty, the runaway continued its high-speed push toward populated towns. If CSX 8888 was going to be stopped, the solution could no longer come from the trackside. Responders had to take the fight directly to the rails. The train was now closing in on the city of Kenton. The tracks here cut directly through the center of the community, crossing busy downtown streets and grade crossings where local traffic had only minutes to clear. CSX 8888 maintained a speed of approximately 51 miles per hour, pulling 2,900 tons of steel and its toxic cargo directly toward these populated areas. Just past the downtown area lay a sharp curve. For railroad dispatchers monitoring the telemetry, this bend was the most dangerous point on the entire route. If a train of this length and weight hit the curve at 50 miles per hour, the lateral forces would likely cause a massive derailment. The tank cars carrying molten phenol, heated to over 200 degrees Fahrenheit, would slide off the rails and rupture, releasing a toxic chemical cloud into the surrounding residential neighborhoods. Every mile the train traveled reduced the available time to react. The window for any safe trackside intervention had completely closed, and the emergency playbook was empty. Ground crews could only watch as the countdown to the Kenton curve was down to mere minutes. If the locomotive reached the curve at its current speed, a catastrophic wreck was inevitable. There was no longer any way to stop the train from the ground. Any successful attempt would have to take place on the moving train itself, out on the active main line. Dispatchers turned to an extraordinary high-risk maneuver out on the main line. Locomotive 8392, a northbound CSX freight engine, had been waiting on a siding to let the runaway pass. Its crew, engineer Jess Knowlton and conductor Terry Forson, received orders to pull out onto the track behind the runaway and give chase. Their goal was not a Hollywood-style collision, but a precise, moving coupling. They had to catch up to a 2,900-ton train traveling at over 50 miles per hour, match its speed exactly, and gently touch couplers without triggering a derailment or destroying their own locomotive. Knowlton pushed his locomotive to 65 miles per hour to close the gap. In the cab, the crew watched the rear car of the runaway grow larger in their windshield. The margin for error was virtually zero. If they hit the runaway too hard, the impact could derail the rear cars, potentially rupturing the chemical tankers located further up the line. If they moved too slowly, they would never catch it before the Kenton curve. Forson stood ready, monitoring the distance. Knowlton eased his engine forward, matching the runaway's 51 miles per hour speed. The two massive machines were now screaming down the track in perfect synchronization, separated by only inches. With a heavy metal clang, the couplers met and locked. The connection was successful. Knowlton and Forson now had a physical link to the runaway, but they still had no control over the lead locomotive's throttle. The air brakes on the runaway's 47 cars remained completely isolated, meaning Knowlton could not use his brake valve to slow the rest of the train. Instead, Knowlton relied entirely on his own engine's dynamic brakes. By switching his traction motors into generator mode, he turned his locomotive into a massive rolling anchor. The resistance fought against the 3,000 horsepower engine of CSX 8888. The wheels ground hard against the rails, as the dynamic brakes absorbed the immense kinetic energy of the runaway. Slowly, the braking force began to win. The speed of the combined consist dropped from 51 miles per hour down through the 40s and then into the 30s. By the time the train neared the crossing south of Kenton, the chase locomotive had dragged the speed down to a manageable 12 miles per hour. At 12 miles per hour, the train was still moving faster than a normal run, but it was finally slow enough for a direct physical intervention. Trainmaster John Hosfeld, who had been pursuing the train along parallel roads, saw his opportunity near the crossing at Route 31. Hausfeld positioned himself near the tracks, waiting for the screaming locomotive to draw near. As the steel nose of CSX 8888 rolled past, he began to run alongside it. He sprinted along the uneven gravel ballast, matching his stride to the 11 miles per hour pace of the train. Reaching out, he grabbed the handrails of the boarding ladder and swung his body onto the steps. He climbed up the platform and pushed open the heavy cab door. Inside, the environment was deafening. The diesel engine was still roaring at maximum revolutions per minute, fighting the drag of the trailing locomotive. The control stand remained exactly as it had been left in the Wallbridge yard. The independent brake handle was fully applied, while the throttle lever was jammed forward into notch 8, commanding full power. Hausfeld moved quickly. He reached for the control stand, grabbed the throttle lever, and pulled it back into the idle position. The roaring of the engine immediately died down. With the throttle closed, Hausfeld then pulled the fuel shutoff valve to stop the diesel engine completely and fully engage the locomotive's brakes. Without the engine's power fighting against it, the combined braking force of the two locomotives took over. The massive wheels ground against the rails, throwing sparks and smoke, before the entire 2,900-ton consist groaned to a complete stop just past the Route 31 crossing. This ending relied on a clear division of labor. The crew on the chase locomotive had successfully used their dynamic brakes to drag the runaway down, bringing it toward a walking pace that made boarding possible. But it took Hausfeld's physical entry into the cab to cut the power source and bring the 66-mile crisis to an end. For the first time in 2 hours, the tracks were silent. The 66-mile crisis ended with no injuries, no derailment, and not a single drop of toxic phenol spilled. But the close call forced immediate reckoning across the industry. The 35-year veteran engineer was disciplined with a 60-day suspension, while Federal Railroad Administration and National Transportation Safety Board investigators scrutinized the events at Stanley Yard. The investigation exposed a series of systemic flaws rather than a simple human error. Investigators focused on the control stand of the EMDSD 40-2, where the physical similarity of the throttle and dynamic brake handles made a mistake easy to commit. In response, CSX retrofitted similar locomotives to physically separate these controls. Railroads also redesigned the cab alerter logic, ensuring that applying the independent brake would no longer silence the safety alarm. Yard operations were overhauled, establishing strict protocols that required double verification before any air-off switching moves could begin. Over the next decade, this incident became a foundational case study in railway safety, accelerating the push for positive train control, a digital system designed to automatically stop a train when human-machine interfaces fail. In 2010, the runaway inspired the Hollywood film Unstoppable. While the movie retained the broad concept of a driverless chemical train and a heroic chase, it fictionalized the scale, names, and action sequences, introducing dramatic near misses and towering bridges that never existed in the flat Ohio countryside. The real-world event was quieter, but far more sobering. It proved how easily a single misread lever, combined with a system lacking a safety backstop, could threaten thousands of lives. While the engineer's action served as the initiating error, attributing the 66-mile crisis solely to individual oversight misses the broader lesson of Stanley Yard. In safety engineering, a single point of failure is any individual component, control, or procedure that can disable an entire system if it fails, without any backup to catch it. On May 15, 2001, the EMDSD 40-2 locomotive possessed exactly that vulnerability. When the engineer pulled the wrong handle, the system did not double-check his intent. Instead, the design allowed a single misread lever to override the train's safety systems, silencing the alerter and feeding maximum power to the traction motors. Human beings, even veterans with 35 years of clean service, will inevitably make mistakes under pressure. A resilient system is designed with the assumption that people will slip up, placing protective barriers between a simple mistake and a catastrophic outcome. In this case, the safeguards did not fail. They worked exactly as designed, yet their layout allowed one operational setting to cancel out another. The independent brake disabled the alerter, and the air-off configuration isolated the train's main braking power. When these independent elements aligned, the entire system lay exposed to one physical movement of a hand. CSX modified its control stands and revised its yard protocols to ensure a single operator's slip could never again release an unmanned locomotive. But the incident stands as a quiet warning for all modern infrastructure. As systems become more complex and automated, we must ask, how many other single points of failure are still out there? Today, modern infrastructure relies on seamless automation to prevent disaster. But safety isn't just about avoiding human error. It's about building systems resilient enough to survive it. As we surrender more control to complex digital networks, the silent threat of a single misread signal remains. How many other single points of failure are still out there?